In 3.2L, I want to more formally talk about how the slope, y-intercept, standard deviation of the residuals, and r-squared are influenced by extreme outliers. In a scatter plot, if we identify outliers, we want to know if they're influential points. So what does influential actually mean? It is that a point, if it is removed, would remarkably change the results of the calculation. In this word remarkably, it's a stronger sense. So just not kind of changing it, but remarkably. So is it an outlier or is it an influential point that's also an outlier? Here's a really good example. We have here the age and months of a child in terms of his or her first word. And then there's an adaptive scale here that gives it a score accordingly. And what we see, for example, here we have child 19 who at about 20 months has an adaptive score of about 121 or 22. If you look at all the data on this scatter plot, right here's the first equation with all 19 children. They've come up with a least squares regression line used to predict, and here's the correlation number. Now, if you look at this, we actually are going to identify child 18 and child 19. So child 18 is way down here, kind of on the x-axis, and child 19 is kind of up here more higher on the y-axis. So in terms of outliers, 18 is more of an outlier on the x-axis movement, 19 is more of an outlier on the y-axis movement. Well, what they first did is they removed child 19. So when you remove child 19, they recomputed and got this is the equation. Notice the y-intercept didn't change much. The slope had a little bit of a change, but the correlation did have a little bit more of a change than the slope did. Now what happens if you keep 19 in there, but now you remove child 18? If you remove child 18, you're going to notice the y-intercept had much more of a dramatic change. The slope had an extremely dramatic change, and the correlation nearly cut itself in half. So this particular outlier right here of child 18 is what we would call as an influential point. Whereas child 19, we would say might just be considered a standard outlier. 18 is dramatically making a difference, so it's influential. So basically what we saw is child 19 was an outlier in the y direction, and removing him or her had little effect on the regression line. Whereas child 18 is an outlier in the x direction, and removing child 18 moves the line quite a bit. It does this because of child 18's extreme position in terms of age. This point has a strong influence on the position of the least squares regression line. Now, a great review point is this. Remember, the least squares regression line makes the sum of the squares of the vertical distance to the points as small as possible. That's why we call it that. And a point that is extreme in the x direction with no other points near it pulls the line towards itself, and therefore we call this influential. Let's go back at that netbook example where we were looking at can weight be used to predict the battery life. If you look at this scatter plot here, this guy right here is about 3.2 pounds and looks like it could be a possible outlier. To see the influence on the least squares regression line, the point's removed and the new equation is computed. So this is the new equation. This here, if you look at it, the slope went from 7.94 to 10.17. So this increased the slope by more than 2. And it actually increased the r squared from 52 to 63. So again, notice this outlier is in more of the x direction, so it's considered an influential point. Well, if we went back to that data, we also had cost. So now what they're going to actually do is do a different scatter plot. Can cost drive the battery life on that? Well, right now, if we look at all this data, it's pretty much spread out. This kind of teal line would be the least squares regression line based on all the data, which gives you this equation up here, where we have a 6.6 y-intercept and a negative slope. But these two guys here in the lower right-hand corner look like they're definitely influential points. If we remove these two, the new line that's going to get created is this pink line, which is incredibly different from the blue one. Here's the new equation right here. The y-intercept is completely different from positive to negative, and the slope is different from negative to positive. So we're going to notice here again how influential those 2 points were in the x direction. Another thing we need to talk about is that association does not imply causation. Just because someone has a strong R or correlation doesn't mean one thing causes the other to happen. Here's a good example. Do fouls increase scoring in the NBA? So what we have in this scatter plot here is the number of fouls a player had in the year versus the number of points, and they plotted a scatter plot. It looks like there might be somewhat of a strong linear relationship. So does that mean the number of fouls, if you have more fouls, is going to imply you're going to make more points? Well, there's a couple things here you want to be cautious of. The first one is that we talked about the direction. There is a strong positive linear relationship. So your gut might be saying, sure, it's going to make a difference. However, you must be logical and cautious. Could a player increase his total points by fouling the ball over more frequently? Sure, if you foul the ball more, maybe you're going to shoot more and then you can make more points. So you have to be cautious. Fouling does not cause the player to score more points. Instead, there is an important lurking variable that influences both variables, the play time. Probably the more times you play, you might have more fouls and you might have more points. It says here, players who are on the court more often tend to score more and have more fouls than those who don't. So really, the number of fouls will not cause your points. It's maybe your play time that may cause you to have more points. Let's just wrap up this chapter with our case closed. Remember in chapter 3, we had the Starnes family going to see Old Faithful, and they had a 4-hour time limit. They didn't know how long they should wait. Well, what they did is he graphed the relationship of the duration of the previous eruption, how long the eruption actually lasted, and the time until the next one. So here's how long the eruptions were, and here's the time until the next one. And it plotted this pattern. And you see it's a strong, positive linear relationship, by the way, with clusters in 2 different spots. When the residual plot was created, you could actually see if this line is good for predicting. Here's the residual plot. Based on this, it seems as though that the least squares regression line does fit the data well. And there's evidence that of random scatter in the residuals. And if you look at this, it says R squared. Which is the coefficient of determination is nice and high. So it does look like there's a linear pattern. So why doesn't the Starnes family find out how long the previous eruption lasted for, put that into the duration, and they can use this to predict, using the model from this, how long they should wait until the next eruption takes place. So for them, chapter 3 would have been a great chapter to know when they went to go see Old Faithful.